Hi everyone, this is Meihui from Class 2 Group 4. I will be representing our group to introduce the models we built for Task 1 and Task 2. Here are our group members and our contributions. For Task 1, we are supposed to predict the number of new deaths in various countries due to COVID-19. To get the prediction, we first chose a dataset including everyday data from many countries on factors like new cases, new deaths, and population from February 2020 to October 2021 to start our modeling process. The large quantity of statistics make it more possible for us to come up with a more accurate model. We can visualize the dataset to verify that there is a strong correlation between the features and the target. Data is also pre-processed to account for the time lag between infection and death due to COVID-19. Here we choose US as an example. After plotting and statistical evaluation, two features are chosen. New cases, modes, and hospital patients are chosen for a multilinear regression. The next step is data cleaning. We remove all the irrelevant terms like null blocks and irrational data to avoid. Then we can split the data into training and testing sets and normalize them before model training. After data is prepared, we feed the model with the training dataset and optimize the parameters using the gradient descent algorithm. Then for model evaluation, we first plot the cost values of the training and testing set. The plot here shows that firstly, the local minimum of cost is achieved at a smooth and stable trend when it approaches the end of the training. And secondly, the overfitting doesn't happen in our model because the orange curve doesn't increase while the blue curve decreases, which means that the validation error doesn't increase when the training error decreases. Then by comparing the cost of different models, we choose the one with the least cost and is the most generalized. After this, we get a prediction of the number of deaths by applying our model to the testing dataset. Using the root of mean square error, we find the model's accuracy. Then closer is it to 0, the more accurate our model is. Here are our plots of the predicted result with the original data. As a result, the value of our MSE of our model is around 72.2, which indicates that there is an error of 72.2 new deaths from the actual value. For task 2, we define a problem as how does movement trend affect reproduction rate of COVID-19. The reason why we decide to focus on the reproduction rate is that as an epidemiological metric was to measure the transmissibility of infectious agents, which is COVID here, it can help the government to decide the timing to open up the restrictions. Since it's difficult and complex to get the value of reproduction rate, if we can build a model which can estimate it based on approachable values, we can help government when it comes to policy making and can save them money and time. For the database, we combine the data from two resources, the reproduction rate from OWID and the movement trend data from Google. Since our code is written in a modular way, it will be easier to build our model based on our countries. So we choose 4 countries for our study, the United States, United Kingdom, Singapore, and Vietnam. Our first step is stacking the feature and data we need from two resources set and combining them. Then the dataset is ready for visualization. Here are the pair plots of all the features and reproductive rate in the 4 countries we chose. Based on the relationship with reproduction rate shown by the plots and the continuous characteristics of the values, we decide to have 12 features to implement multilinear regression of our model. 6 original features with the other 6 being the exponential version of the original features. This is because the plots indicate that there is an exponential relationship between the features and the targets. After this, we split and prepare the data for these features and target columns of our model training. Since more training data will help to produce a model with higher accuracy, we want the training data to be larger than that of the test data. At the same time, we still want to retain a significant portion of the model to test its ability to generalize to unseen data. Hence, we decide to split 30% of the data to be testing, and the rest 70% will be used to train the model. The splitting is random to avoid bias, and the random state is set as fixed to do a meaningful comparison between different models. By using the same cost function and gradient descent algorithm in task 2, we can get the parameters of our linear model. Once we get the model, we can use the testing set to evaluate it. For the same reason of in task 1, we can see that local minimum is already achieved and the overfitting doesn't happen in our model. Here are the plots of the predicted results we derived from the testing data using our model with the original data. We still use the root of the mean square error to reflect our model's accuracy. When the model is trained on model movement trend in the UK in 2021, the RMSE value is 0.146. Although RMSE is small, it's due to the small range that RMSE values usually take on. Hence, although the model has a low RMSE value, there are further improvements that can be made. So for the errors in these two models we built, we think there are a few underlying reasons for them. First, by comparing the models of countries with different strategies, we found that our approach of using movement trends to predict reproduction rate is not effective in every country. In countries that apply zero-COVID strategy like Singapore and Vietnam, because of the strict border measures and cleanness of COVID in community, the reproduction rate will not increase when people go to public spaces, which indicates that movement trends might not be a good predictor here. However, as more countries in the world are accepting the live with COVID strategy, this model has a potential for a wider application. Secondly, the features that do not show a clear relationship with our target are not included in our consideration. But they may also have influences on our target or other features. Without considering these impacts might lead to errors in our models. Thank you.